Hello friends, so welcome to the 35th lecture of this course, and in this lecture I am going to introduce an application of line integral that is called work done. So, let V be a, so V let the components of V are V1 x y z in I direction, V2 x y z in j direction plus V3 x y z in k direction. So, let V be a vector function which is defined and continuous on a piecewise smooth curve C. So, V is a vector function which is continuous on a piecewise smooth curve C. So, let us put simple piecewise. Then the integral of the tangential component of V along the curve C from a point P to a point Q is given as. So, this is given by a line integral and it will be something like this, integral P to Q and then V dot dr. Let us define C star. So, C star is the arc of curve C from point P to Q, then it will become V1 dx plus V2 dy plus V3 dz. So, this is the integral of tangential component of V along the curve C from the point P to Q. Now, based on this we are going to define the work done. So, let V the vector function equals to F, which is a variable force acting on a moving particle So, this moving particle is moving along the simple piecewise smooth curve C, and this force F is acting on this moving particle. Then the work done by the force F in moving particle from a point P, which is a point on the curve C, to a point Q is given as, so work done W is given by the line integral P to Q, the force vector F dot dr. So, this is the same integral, or I will say the same line integral which is we have taken for the integral of tangential component of V. And this is if F is having the components F1, F2 and F3, means F is defined as F1i plus F2j plus F3k, where F1, F2 and F3 are functions of x, y and z, then it will become again C star F1 dx plus F2 dy plus F3 dz, where C star is the arc of the curve C from the point P to the point Q. Now, we are going to take few examples of work done, and then we will see that what will happen if the force vector F is a conservative force vector, means there exists a potential function phi such that the vector function F equals to gradient of phi. But before that, let us take some simple example. So, example 1. So, find the work done by the force F, that is 8x square yz I plus 5zj minus 4xy k. In moving a particle over the curve y equals to x square and z equals to x cube. So, this is the curve in 3-dimensional space from, let us define our point P and Q. So, let us take P as 0 0 0, one 1 1. So, first of all, as we have done in line integral, we need to find out the parametric representation of the curve C, and then only we can evaluate the line integral. So, let x equals to t, then y will become t square and z, which is x cube, will become t cube, where t is in closed interval 0 to 1. So, the parametric representation of the curve C is RT equals to Ti plus T square j plus T cube k, and t is between 0 to 1. Now, if I calculate dr over dt, it will become I plus 2tj plus 3t square k. Now, work done, and here the force F in terms of t given as 8 times x square will become t square, y will be t square and z will be t cube. So, total will become t raised to power 7 I plus 5z. So, 5z means 5 t cube j minus 4 x is t, y is t square. So, 4 t cube k. So, now work done is given as from the point P to Q, line integral, that is f dot dr. So, it will become P to Q f dot dr over dt into dt. So, it will be 0 to 1, the limit of the t, f dot dr will become 8 into t raised to power 7 plus 5 into 2 10, and here I am having t cube, here I am having t. So, 10 into t raised to power 4 and then minus 3t square here, 4t cube here. So, the total will become 12 t raised to power 5 and then dt. So, this will become t raised to power 8 plus 2 t raised to power 5 minus 2 t raised to power 6, and that is 0 to 1. So, it will become 1 plus 2 minus 2. So, this cancel out 1. So, the work done is 1. For moving the particle by the force F along this curve y equals to x square and z equals to x cube from the point 0 0 0 to 1 1 1. So, this is simply represented by a line integral. Now, let us see the work done in case of conservative vector field. F. So, let F be a conservative vector field. This means there exists a scalar function phi x y z such that f equals to gradient of phi, means phi is a potential function of the vector field f. Now, work done W is P to Q f dot dr. So, it will become P2Q f1 dx plus f2 dy plus f3 dz. Now, this f equals to grade of phi. So, hence this f1 equals to del phi over del x, f2 equals to del phi over del y, f3 equals to del phi over del z. So, this is equals to P2Q del phi over del x into dx plus del phi over del y into dy plus del phi over del z into dz. And this will become P2Q d phi, and if I integrate it, it is simply phi xyz P2Q, that is phi q minus phi p, and hence what we can conclude that the work done depends only on the initial point and the terminal point, means on the point q and the point p. It is nothing to do with the path moving from p to q, means the work done or line integral in case of conservative vector field is path independent. You go along any path. So, if this is P, this is point Q, you move like this, you move like this, you move like this, you move along a straight line, or you move like this, or you move any other path, because there will be infinitely many paths between P and Q. Along all the curves, integral will be same in case of conservative vector field, and that is the idea mentioning here, that work done in case of conservative vector field. So, if question is like that, let f be a conservative vector field given by this, then find the work done by this conservative vector function or conservative force by moving a particle from P to Q. So, what you need to do? You need to find out the potential function phi corresponding to conservative vector field f, and then phi q minus phi p, that is all. Let us take an example of this case. So that the force vector f, which is given as yz minus 1 I plus z plus xz plus z square j plus y plus xy plus 2yz k is conservative. Also find the work done by f in moving a particle from 1 2 2 2 2 3 4. Okay. So, in the first sentence of the question, I need to show that the force vector is a conservative vector field. This I can do using 3 methods. Let us take method 1. If f is conservative, means f equals to grade phi, and curl of grade of any scalar function is always 0. So, if curl of f is 0, means f is a conservative vector field. So, calculate curl of f. So, it is given by I j k del y del x del by del y, and then y z minus 1 z plus x z plus z square y plus x y plus 2 y z. So, this equals to I, and then del by del y of this function. So, 1 plus x plus 2 z minus del by del z of this function. So, minus 1 minus x minus 2 z plus j component. So, del by del z of this function. So, y minus del by del x of this function. So, y minus y plus k component. So, del by del x of this. So, it will be z minus z. So, it comes out to be 0. So, curl of f is 0. So, f is a conservative vector field. Method second. You know that f is, let us say, f1i plus f2j plus f3k, where f1 is yz minus 1, f2 is z plus xz plus z square, and f3 is y plus xy plus 2 yz. Now, it is equals to grade of phi. So, it means del phi over del xi plus del phi over del y j plus del phi over del z k. If f is conservative, these two are equal. It means f1 equals to del phi over del x and f2 equals to del phi over del y and f3 equals to del phi over del z. Relation 1, relation 2, relation 3. Let us differentiate partially relation 1 with respect to y and relation 2 with respect to x. So, what I will get in this case, del f1 over del x, no del x, I am doing first with respect to y. So, del f1 over del y, this equals to del 2 phi over del x del y. Now, differentiate partially relation 2 with respect to x. So, I will be getting del f1 over del x, this will become del 2 phi over del x del y. So, right hand side equal. So, from here I got del f1 over del y equals to del f2 over del x. Similarly, what you do? You differentiate partially the second relation with respect to z and the third relation with respect to y. So, what you will get? Del f2 over del z equals to del f3 over del y. And then what you do? you differentiate first relation with respect to z partially and the third relation with respect to x partially. So, what I will get, del f1 over del z equals to del f3 over del x. So, if the components of a vector field satisfy these three equalities, then the given vector field is a conservative. And if you see in this example, all these three conditions are satisfied and hence you can say that f is conservative. My third way of is to find out the potential function phi such that f equals to grade phi, and if I do it, phi comes out to be in this case for this vector field as x y z minus x plus y z plus y z square plus constant c. And if you see that del phi over del x will become y z minus 1 f1 component, del phi over del y will become x z plus z square means f2 component, and similarly del phi over del z will become y plus xy plus 2 yz, that is the f3 component. Now, work done is one, two, 3, 4, f dot dr. Here curve is not given, but just now we have proved that it will become phi of 2, 3, 4 minus phi of 1, 2, 2, since f is a conservative vector field and this comes out to be 67. So, in this way we can solve this kind of example where the force vector is a conservative vector field. Okay, there are some more facts I want to tell you, that if f is a conservative vector field, then the integral over a curve C f dot dr is independent of the path. We have seen just in this example and we have proved it earlier. If f is continuous vector field on an open connected region D, and if the line integral over a curve C f dot dr is independent of path for any path in domain D, then f is a conservative vector field. The third remark I would like to tell you, that the line integral over a closed curve C, if this line integral, that is f dot dr, is 0, then f is conservative, because in case of closed curve the initial point and the terminal point will be the same, and hence we are subtracting the same amount from the same amount. So, it must be 0. Finally, if f dot dr equals to 0 over a closed curve C for every closed path C, then f dot dr is independent of path. So, with these remarks I will end this lecture. So, in this lecture we have learned the concept of work done, that is basically representation of line integral. So, if someone asks you what is the physical representation of a line integral, you can say that it is work done. So, thank you very much.